Hello, we are Group 7. This is Project 3. It was created by myself, Joe Riddell.
Reed Johnson.
And Aiden Passmore.
What is cold working? Cold working, or also known as work hardening, is the process of shaping a material without heating. An example of cold working would be cutting with a blade, bending, drawing through a die, or stamping. Now let's talk about what cold working does on a molecular level. Cold working causes deformations in the grain structures, which this leads to dislocations. Dislocations are also known as line defects, create a network in the grain, and this network increases the hardness, but does make it more brittle or decreases the ductility. What is annealing? Annealing, or heat treating, is the process of heating a material to a specific temperature and then cooling it down slowly. This can be done using induction heating, kilns, or torches like gas. What does annealing do? When annealing, the increase of heat causes the molecules to vibrate more. This increased energy causes it to move around and the defects and dislocations to be filled back in. This then increases the ductility, but then decreases the hardness that you gain from cold working. The numbers behind cold working. So we took two test strips and put them under a tensile test. And we tested the hardness at the unworked section, part that was unfazed by the tensile testing, and then the worked section, which is where the necking happened and there was some deformations, plastic deformations. And as we can see with the aluminum, it had a hardness rating of the unworked section 9.0, and the hardness of the worked section, the necked part of the test strip, is 10.7. As for the steel, the unworked section, the untouched part, had a hardness of 48.5, while the worked section, the part that necked and had deformation, had a hardness of 80.9. So this is the part of the presentation where I would talk about the numbers of annealed metals. But unfortunately, as you can see here, we have no numbers. This is because our annealing furnace is out of operations right now, and we were unfortunately unable to complete that part of the process.
Hello, my name is Reed Johnson. In this section, we're looking at using cold working and annealing to work steel into something that has a percent ductility of 15% and a tensile strength of at least 800 megapascals. The sample that we're working with has a starting diameter of 5 centimeters, and we want to work it into a cylinder with a diameter of 3 centimeters. So to start this process, we're going to look at the percent area reduction. The most general formula for that would be pi times d naught squared over 4 minus pi times df squared over 4 all over pi g naught squared over 4. You can do some algebra, and this will simplify down to 1 minus d naught squared over df squared. When we plug in our numbers, we end up getting 1 minus 9 over 25, which gives us a percent area reduction of 0.64, which equals 64%. Now we can look at this set of graphs to try to figure out the percent cold work that we actually want. So if we take a look at this graph, we want a tensile strength of at least 800 megapascals, which is right here. if we draw a line down, we're looking at a little bit over 10% cold work, about 12% cold work. Um, but we also want to make sure we have at least 15% ductility. So we're going to do the same thing on this graph over here. We're going to find our 15% ductility. We're going to draw a line over, and then we'll draw the same line down. And we'll see it's in about the same spot, 12%. Now, unfortunately for us, the tensile strength of steel increases with cold working, while the percent ductility decreases with cold working. So this is the only point that they overlap, and we have to use 12% as our value. We're gonna have to break this into two parts. First, we're gonna do our cold working and get it close, but not quite to the 64% reduction area. Then we're gonna anneal it, and then we're gonna do more cold working to get it to the 64% reduction area and 12% cold working. So to find the first value that we're gonna cold work to, we're gonna take our 64% minus our 12%, and we're gonna get 52%. Now we're gonna take that 52% and we're gonna plug it back into our area reduction formula, but instead we're gonna be solving for D. So we're gonna have 1 minus D squared over 5 squared equals 0.52. And we're going to solve for D, and that'll tell us how much we need to cold work the sample first before we anneal it. So we can just add the D squared over 5 squared to the other side and subtract the 0.52. And then we get 1 minus 0.52 equals D squared over 5 squared. Rearranging some more, we're left with D equals the square root of 5 squared times 1 minus 0.52. And all that equals 3.461. So we're going to cold work our sample and tell this diameter of 3.461 centimeters. Once we're done with our first round of cold working, we're going to anneal the sample to reset any internal changes that we've made along grain boundaries and dislocations, which will end up resetting the ductility and resetting the tensile strength. Then we're able to cold work the last 12%, which is the percent cold work that we want. And after we do that, we end up with a ductility of 15% and maximum tensile strength of 800 megapascals.
Hello, I'm Aiden, and I will be using the same process that Reed used for the steel, except for aluminum this time. So to start it off, we need to start to find the percent area reduction, which can be simplified as D naught over D final squared, which is going to be, or sorry, 1 minus. So it's going to be 1 minus 9 over 25, which is going to leave us with 0.64, which is equivalent to 64%. And then using this, we can apply our knowledge of the relationship between the percent area reduction and the percent cold work to find the percent cold work to be around, sorry, to be around 64% as well. And then using this, I can plug in the graph I got for aluminum to find that the final one, if we use the 12% that Reed found for steel to be around here, sorry, to be around here, we get a percent elongation that would end up being around, say, 10-ish percent, and a tensile strength of around, we'll say 130 megapascals. But in order to do that, we have to go through the math first to show how we got there. In order to get a final diameter of 3 and a final percent cold work of 12%, we can treat it as if we had elongated it to a certain point and then annealed it to reset the percent cold work, and then we elongated the final 12% to get the values needed. So in order to do that, we can set it up as 1 minus 3 over x squared equals the 0.15, which is the 15% left. So in order to solve for that, it's just going to be 0.85 equals 9 over x squared, which is going to leave us with x equaling 3.461 roughly. And then using that value, we would then elongate it, stretch it out to get our final value of the diameter being 3. So d final equals 3. And then plugging that in, as I said, percent cold work of the final is going to be about 12%, which is going to be a straight line running roughly around there. And then we get our final elongation value, or the ductility is going to be, we'll say it's going to be 60%, or sorry, not 60%. It'll be 10%. And then the tensile strength is going to be 135 megapascals.